going to sum up a lot of stuff. By the end of today, you'll be reminded all about exponential functions. You'll also be able to find derivatives of exponential functions and integrals of exponential functions. So, let's jump right in. Couple rules. If we have a function in the form of f of x equals a to the x, it is an exponential function. If x equals 0, then a to the 0 is 1. If x equals negative n, then we can move it to the denominator to make it positive. And if you have a fractional exponent, the top is your power, and the bottom is your root. So a to the p over q is the same thing as the qth root of a to the p, or the qth root of a quantity to the p. So either of these will work. Meaning, you can take it to the power or the root first, whichever order you'd like to do it. If x is rational, the graph of a to the x will always be graphed like this. If a is any positive number, we define a to the x being the limit as r approaches x of a to the r. And r is a rational number, so your graphs will roughly look like this. So, laws of exponential functions, given that a is positive and not equal to 1, a to the x is continuous with domain, all real numbers, and range 0 to infinity, not including 0. You can see that from this graph here. Domain, all real numbers, range 0 to infinity. So a to the x plus y could be written as a to the x times a to the y, because when we are multiplying the same basis, we add our exponents. A to the x over a to the y. This one, power to a power, we can multiply those. And when we have a product to a power, each base gets that power. Now, I apologize for these equal signs that should be there. Get rid of those. Shouldn't be there. So, if I look when a is positive, like these two examples on our graph are, one's 4 to the x and one's 2 to the x, 4 and 2 are both positive. As we approach infinity of either of those functions, our graph goes to infinity. If we approach negative infinity with either of those functions, our graph goes to 0. So that's something you're going to want to remember. When a is positive, your graph looks roughly like this. Now, when a is negative, a little bit different. I apologize for those extra equal signs. When a is negative, that reflects our graph over the y-axis, and as we approach infinity, we are now approaching 0. And as we approach negative infinity, we are now approaching infinity. Find the limit as x approaches infinity of 2 to the negative x minus 1. So, let's talk about this for a second. I can break this up to be the limit as x approaches infinity of 2 to the negative x minus the limit as x approaches infinity of 1. I'm going to rewrite this. Limit as x approaches infinity of 1 over 2 to the x minus the limit as x approaches infinity of 1. Well, the limit as x approaches infinity of 1 is 1. It's a horizontal line, so it's always going to be approaching 1. The limit as x approaches infinity of 1 over 2x is similar, except that if we think back to these graphs, another way we could write this is the limit as x approaches infinity of 1/2 to the x. So it's a situation where a is between 0 and 1, which means it looks like this graph. And when we approach infinity, we get 0. Minus 1 gives us negative 1. Now, we're also going to introduce a number to you that you've seen before, but you may not remember what it equals, and it is the number e. E is technically equal to the limit as x approaches infinity of 1 plus 1 over x all to the x power, or it is the summation from 0 to infinity of 1 over n factorial. E is approximately equal to 2.71828182845904523536. Do I expect you to know all of those digits? No, but you should probably know the first 5 decimal places at least. You learn the first 5, the first 9 are easy, but know approximately what that number equals. Now, derivatives of natural exponential functions. If I were to sketch the derivative of this function, think slope. So over here, I have small positive slopes, and then I have bigger positive slopes, and then I have bigger and bigger positive slopes. And you'll notice that my derivative is identical to my original equation, which tells us that the derivative of e to the x is itself e to the x. Derivative of e to the x is e to the x. So let's try something. If I were going to derive y equals e to the tangent of x, and we're finding the derivative, we've got e to the tangent of x, because the derivative of e to anything is itself. But then we need the chain rule in this case, because the tangent of x is in our exponent. The derivative of tangent of x is secant squared x. So maybe a better way to write this would be secant squared x times e to the tangent of x. Next one, same idea, only it's going to combine the product rule with the chain rule. So if I'm going to derive this, we know we need the product because we have two things multiplied that both have a variable. And I need the first, e to the negative 4x, times the derivative of the second. And the derivative of sine of 5x is cosine of 5x times 5. Using the chain rule, the derivative of 5x is 5. Plus the second, sine of 5x, times the derivative of the first. The derivative of e to the negative 4x is e to the negative 4x. Derivative of negative 4x is negative 4. So if I write this a little bit nicer, cosine of 5x e to the negative 4x, and actually, not typically how they write them. Typically, constant e trig function. E to the negative 4x cosine of 5x minus 4 e to the negative 4x sine of 5x. All right. Integration, since e to the x has its own derivative, it also has its own antiderivative. So the integral of e to the x to the dx is e to the x plus c. E to the x plus c. Let's try one. So I want to find the indefinite integral of that function. I'm going to need u substitution, and I'm going to make my u x cubed, which means du dx is equal to 3x squared, and du over 3x squared equals dx. So now let's plug in what we know. We've got the integral of x squared. E, instead of x cubed, I'm going to put my u because u equals x cubed. Dx is now equal to du over 3x squared. If you watch closely, my x squared will cancel out, and I can pull my 1/3 out front because it's a constant. At this point, we can antiderive. And the antiderivative of e to the u is e to the u. Indefinite, so we need a plus c, but we can't leave a u in our answer, so really we've got 1/3 e to the x cubed plus c as our answer. Let's try one more example. It says find the area under the curve y equals e to the negative 3x from 0 to 1. So we're talking about the integral from 0 to 1 of e to the negative 3x dx. We're going to need another u. My u is going to be negative 3x. Eventually you might get good enough at this that you don't have to use the u and you can still figure out what's going on. The derivative is negative 3, which means du over negative 3 equals dx. We have the integral from 0 to 1 of e to the u times du over negative 3. And I can make that negative 1/3, 0 to 1, e to the u du. Now be careful, the 0 and 1 are x coordinates. So if I antiderive e to the u, I get e to the u. But u isn't really u. It's negative 3, and I need that negative 3x. And I need that from 0 to 1. So I end up with negative 1/3 e to the negative 3 times 1 minus negative 1/3 e to the negative 3 times 0. So negative 1/3 e to the negative third plus 1/3 e to the 0 is 1. And that's our answer. So look this over, watch it closely. If you have other questions, please bring them to class tomorrow.